Welcome back to the deep dive. Today, we are tackling a problem that I think genuinely pauses this sort of low-level panic in most of us.
Oh, yeah.
You wake up, you check your phone, and there it is, the wall of text.
It's the defining feature of the information age, isn't it?
Yeah.
We have access to the sum of human knowledge, but we're just drowning in it.
We are. I mean, our bandwidth hasn't changed since the Stone Age.
Not at all.
Between the emails, Slack, news alerts, and those, 50-page reports that could have been an email, we are all just desperate for a button.
The TLDR button.
The tell me what matters button, exactly. And today, we are diving into the technology that is trying to build that exact button.
We're talking about automated text summarization.
Right. And looking at the research you pulled, the first thing that really surprised me is that this isn't some, byproduct of the ChatGPT era. This goes way back.
Oh, much further. If you trace the lineage, this is actually one of the founding challenges of computer science. We're talking about the late 1950s.
That's wild. I mean, we barely had computers that could do basic math, let alone read.
True, but the need was already there. You had the Cold War, a massive explosion in scientific publishing, and researchers like H.P. Loon at IBM in 1958 were already thinking, we cannot physically read all of this. We need a machine to do it for us.
So Loon and then Edmondson in the 60s, they sort of laid the groundwork, but then the history goes a little quiet.
It does. There was a bit of a hiatus. The theory was Sound Loon essentially invented the logic we still use today.
Yeah.
But the hardware was the bottleneck.
Ah.
It wasn't until the internet exploded, giving us these massive data sets and the processing power to crunch them, that the technology finally caught up to the ambition.
So the mission for this deep dive is to unpack exactly how that technology works. How does a pile of silicon take 1,000 words, strip away all the fluff, and leave you with the 100 words that actually matter?
And we're going to do this by following the pipeline. Essentially, following a document as it gets fed into the machine, chopped up, analyzed, and then reassembled.
I like that. But before we start the conveyor belt, we need to agree on what a summary actually is, because the source material gives a surprisingly rigid definition.
It really does. It's not just make it shorter.
No, the definition is a text produced from one or more original texts that contains a significant portion of the information, but is no longer than half of the original length.
That half is the hard constraint.
Yeah.
You take a 1,000-word article, cut it to 900 words. That's not a summary.
You've just edited it.
You've just edited it. You have to aggressively compress the signal.
And within that definition, there are two flavors. You've got indicative and informative.
Yes, and this is all about function. An indicative summary is like a movie trailer.
Okay.
It tells you what the text is about, but it doesn't give you the ending. This report discusses the Q3 financial losses.
It helps you decide if you even want to read the full thing.
Exactly. Whereas an informative summary, that's the spoiler, it replaces the original. Q3 losses were $10 million due to a supply chain crash. You read that, you don't need to open the document.
Got it. Which brings us to the central conflict in this whole field, the battle between extracts and abstracts.
This is the big one. It's the distinction between, let's say, copy-paste and actual writing. An extract is what you did in high school when you were lazy. You highlight the best sentence in paragraph 1, the best sentence in paragraph 2, and you just string them together.
You're not generating anything new. You're just curating.
Precisely. And for a long, long time, that was the only way computers could do it. It's safe, right? You know the grammar is correct because a human wrote those original sentences.
But the abstract, that's the holy grail.
That's the one. An abstract is when the machine reads the text, understands the concepts, and generates brand new sentences to explain them. It digests the information and regurgitates it in a new form.
Infinitely harder, I'd imagine. So let's get into the mechanics. Stage 1 of the pipeline, topic identification.
Or, as you put it, how the computer picks the winners.
Yeah.
It really is just a scoring game. Imagine the computer looks at a document, it breaks it down into units, usually sentences, then it has to assign a numerical score to every single one.
And the top 5 scorers make the team. The rest get cut.
Exactly.
But here's the problem. The computer doesn't know what the words mean. It doesn't know that bankruptcy is important or that coffee break is, trivial.
So what criteria does it use to keep score? It uses proxies for importance.
Right.
And the oldest and surprisingly reliable proxy is certainly position.
Location, location, location.
Especially in news. Think about how a journalist writes.
The inverted pyramid, the lead, the first paragraph has all the juice.
Precisely. There is actually something called the optimum position policy, or OPP. Research shows that for news articles, the first sentence of a paragraph is the winner about 85 to 90% of the time.
So you're telling me if I just built a bot that copied the first sentence of every paragraph, I'd actually have a B-plus summarizer.
For news, yes. For scientific papers, it might look for headers like conclusion or results. But you can't rely on structure alone, so the machine also hunts for cue phrases.
These are the tells, right? The giveaways.
Right. Researchers like Teufel and Moens cataloged over 1,400 of these phrases. Things like, in this paper we show, or the significant finding is, or
In conclusion.
in conclusion. It's like a dog hearing the word walk. The computer sees the main point is, and its ears perk up. That sentence gets a huge point boost.
Okay, but those are the easy ones. Now we get to the math. Word frequency. This goes back to Loon, and it relies on something called Zipf's law.
It does.
And I want to dig into this because Zipf's law sounds cool, but if you just count the most frequent words in a document, aren't you just going to get the or and 500 times?
That is the catch. Zipf's law states that a very small number of words appear very frequently. The, of, is, and a huge number of words appear very rarely.
Right.
The high-frequency words are just noise. They have no resolving power.
So the computer ignores the top of the list.
It ignores the top, and it ignores the very bottom words that appear once are usually outliers. It looks for the Goldilocks zone.
Okay.
Words that appear with unusual frequency in this specific document compared to general language.
So if I'm reading a general news site, the word mycelium is rare, but if I open a document and mycelium appears 40 times...
Then mycelium is a keyword. And any sentence containing that keyword gets a score boost. The more keywords a sentence packs in, the higher its score.
That makes perfect sense. It's keyword density.
And you can layer on more sophisticated metrics like connectedness. This uses lexical chains.
Is this where the thesaurus comes in?
Yes, basically. The system looks for relationships. If sentence A talks about cars, sentence B talks about automobiles, and sentence C talks about Ford, the computer recognizes a chain. It draws a web between these sentences.
And the sentence that sits in the middle of that web?
Is the central sentence. It has the highest connectedness score. It's like the center of gravity for the document.
So you have all these scoring methods, position, cues, Zipf's law, connections. The best systems just sort of mix them all together.
They do. They use Bayesian classifiers or other machine learning models to weigh these factors and spit out a final score for each sentence. And interestingly, the research suggests there's a real sweet spot for how much you should keep.
A length limit.
A compression ratio. Summaries are most useful when they're between 15% and 35% of the original length.
Okay.
If you go shorter, you lose context. If you go longer, you aren't really saving enough time.
15 to 35%. That's a good rule of thumb. Okay, so we've scored our sentences, we've picked the winners. If we stop here, we have an extract. But we want to get to the abstract. We want the machine to actually understand. This brings us to stage 2, interpretation and fusion.
And this is where the machine hits a brick wall called the semantic gap.
The source material used the sour grapes analogy for this, which I thought was brilliant.
It's the classic Aesop fable, right?
Yeah.
The fox jumps for the grapes, fails to reach them.
And walks away saying, they were probably sour anyway.
And we as humans immediately get the subtext. He's jealous, he's rationalizing his failure.
Of course.
If you ask a human to summarize it, they'd say, the fox pretended not to want the grapes because he couldn't have them. That requires world knowledge. You have to understand psychology.
But the computer just sees the data points. Fox, jump, fail, walk, speak.
Exactly. It lacks the background framework to interpret sour grapes as a psychological concept. And that's why abstractive summarization is so hard. The machine can't easily say why something happened, only that it happened.
So how do they cheat? Because they do have workarounds.
They have to. One way is something called topic signatures. This is a form of compression by categorization.
Give me an example.
If the computer sees the words bat, pitcher, ball, home run, and stadium, it can map all of those to a single head word or concept, baseball.
So it swaps out the list for the category.
Yes, it compresses the text by raising the level of abstraction. Instead of listing every ingredient, it just says dinner.
And the other workaround is guided summarization. This is where we stop trusting the AI to figure it out and just hand it a template.
This is very common in specific fields, like disaster reporting. We tell the system, I am feeding you news about an earthquake. I want you to find and fill in these blanks. Magnitude, location, death toll, date.
It's like painting by numbers.
It is. It's highly effective because it guarantees you get the key facts. But it also means the summary is strictly limited by the template if something totally unexpected happens.
Like the earthquake reveals a hidden city or something?
Exactly.
Yeah.
The template might miss it because it wasn't told to look for archaeology.
That is a big limitation to keep in mind, but okay, let's assume the machine has identified the topics. Now comes the part that usually goes wrong. Stage 3, generation,
Actually writing the sentences, this is where we fight the disfluencies.
which is just a polite way of saying Frankenstein text.
It is. If you just cut and paste sentences from different paragraphs, they don't flow. You get dangling pronouns.
Right, like a summary that starts with, he denied the allegation.
Who is he? What allegations? The he refers to someone mentioned 3 paragraphs ago who didn't make the cut. So the system has to perform smoothing.
And there are some really cool methods for this. Let's talk about text compression first, the Knight and Markham method.
This one relies on the parse tree. So imagine a sentence structure like a tree. The trunk is the main noun and verb. The branches are adjectives, dependent clauses, all the extra details.
So the system literally prunes the tree.
It does. It identifies the branches that aren't structural, like the very angry dog becomes just the dog. It strips away the decoration to leave the load-bearing beams of the sentence.
And that shrinks the sentence so you can fit more facts into your 15% limit.
Precisely.
But the most sci-fi sounding method has to be sentence fusion, the lattice method.
Ah, Barzilai and McKeown. This is fascinating. This deals with the problem of having multiple sentences that say basically the same thing.
Like what?
Sentence A, the troops entered the city. Sentence B, soldiers marched into the capital. Sentence C, the army breached the town.
They all mean the same thing, but the words are different.
Right. So the computer aligns them. It matches troops to soldiers to army. It matches entered to marched to breached. Think of it like stacking 3 transparencies on top of each other and pinning them where the meanings overlap.
That creates a web or a lattice.
Exactly. And then the computer traces a brand new path through that lattice. It might generate, the army marched into the city. That specific sentence didn't exist in any of the original documents.
Wow.
It is a fusion, a brand new creation.
That is the ghostwriter moment. It's actually writing, not just copying.
It is. And that technology is absolutely critical when we step up to the real challenge, multi-document summarization.
Because so far, we've just been talking about summarizing one report. But the real nightmare is when you have 50.
A news story breaks. You have reports from Reuters, AP, CNN, the BBC. They are all covering the same event. If you just run a standard extraction on that pile, you're going to get a summary that says,
The fire started at 9.
the blaze began at 9 p.m.
At 9 o'clock, a fire started.
Exactly. Repetition becomes the enemy. And contradiction. One report says 10 dead, another says 12, one is from Tuesday, one is from Wednesday.
So how does the system filter the noise when the noise is echoing?
It uses a logic called MMR, maximum marginal relevance.
Okay, let's unpack MMR because the math here is actually really intuitive. It's a balancing act.
It is. The algorithm has 2 opposing goals for every sentence it considers. Goal 1, relevance. Is this sentence on topic?
Does it have the keywords?
Right. Goal 2, novelty. Is this sentence different from what I've already put in the summary?
So as it builds the summary, it's constantly looking back at what it just wrote.
Yes. It actively penalizes similarity. So let's say the system picks that first sentence. The fire started at 9 p.m. Now it looks for the next sentence. It finds another one that says, the blaze began at 9. Because those 2 are semantically similar, the second sentence gets a massive penalty score.
It gets downvoted because it's redundant.
Exactly.
Yeah.
So the system is forced to look for a sentence with high relevance but low similarity to the first one. Maybe something like, the fire department arrived at 9:30.
It's like a good dinner party guest. You don't just repeat what the last person said, you add to the story.
That's a perfect analogy. And this memory is essential for update summaries. Think about News Blaster or Google News. If you read the news at 8 a.m. and then check again at noon, you don't want to read the 8 a.m. stuff again.
You just want the delta, the changes.
Exactly. The system has to maintain a history of what you've seen, subtract that from the current stream of news, and only summarize the remainder.
It's just incredible how much logic goes into just giving me the gist. But this brings us to the final, and honestly, the most headache-inducing question of all. How do we know if the machine did a good job?
The evaluation
Well,
problem.
even humans can't agree on this. If I ask you and our producer to summarize the same movie, you're going to give me 2 totally different summaries. Neither is wrong.
That is the subjectivity issue.
Yeah.
There is no single gold standard. So researchers have to split evaluation into 2 camps, intrinsic and extrinsic.
Intrinsic is looking at the text itself. Is the grammar good?
Yes. Does it flow? Is it readable?
And extrinsic is about utility.
Right. Does it help you do a task? For example, if I give you the summary of a medical report, can you correctly diagnose the patient without reading the full text? If yes, the summary worked.
That makes sense. But you can't do that for millions of summaries. You need an automated way to grade the homework.
Enter ROUGE.
ROUGE. What does that stand for?
Recall-Oriented Understudy for Gisting Evaluation.
Wow. They really forced that acronym.
Computer scientists love a good acronym. But the key word there is recall. ROUGE compares the machine summary to a set of human-written summaries.
And it looks for n-grams, which are just sequences of words.
Basically, yeah. It's checking for overlap. It
Yeah.
asks, how much of the content that the humans thought was important did the machine also catch?
So if 5 human summarizers all included the phrase economic downturn and the machine missed it, the machine gets a failing grade.
Correct. And the pyramid method takes this even further. It visualizes the facts as a pyramid.
Walk us through the pyramid.
You take those 5 human summaries, you analyze them for summary content units, basically individual facts. If a fact appears in all 5 human summaries, it goes to the very top of the pyramid. It is essential.
And if a fact only appears in one summary?
It goes at the bottom. It's optional detail. When you grade the machine, you give it way more points for catching the facts at the top of the pyramid than the bottom.
It's weighting the facts based on human consensus.
Exactly. It's trying to mathematically model importance.
It's really amazing to see how we've moved from simple word counting in the 50s to these complex sentence fusion lattices and pyramid evaluations.
It is. And as the volume of data just keeps growing, these tools aren't luxuries anymore. They're becoming the primary lens through which we view the world.
Right.
We can't read everything.
So we rely on the summary, which brings me back to something you said earlier about guided summarization. The templates.
Yes.
We talked about how machines have the sour grapes problem. They can't understand intent, so we give them templates to look for death toll or stock price to make sure they don't miss the point.
Right, to guarantee you get the key facts.
But I want to leave the listener with this thought. If we are relying on templates to tell the machine what to look for, aren't we just creating a feedback loop?
That is the danger. If you tell the machine, find the financial data, it will find the financial data. But if the real story was a human drama, or a bizarre coincidence, or something that didn't fit the template,
The machine will just ignore it.
it will ignore it.
We get the data we asked for, but we might lose the actual story.
You get a summary of your own expectations.
That is something to think about the next time you hit that summarize button. Are you reading what the author wrote, or are you just reading what the algorithm was told to find?
Always a good question to ask.
Thanks for diving in with us. We'll see you on the next one.